Okay. Okay, so looks like nobody has tried it. Anyway, it is all sorted since we had went through a lot of trouble of defining a system. So let's jump to some of the slides of previous class, and then we'll try to work it out. So what I'll do is maybe I'll just open it first. You're able to see? These are all the system data that we generated randomly. So in this case, so if you look at this, location of loads and parameters of loads is there. So if you remember, we had developed some time back a Y-bus building algorithm. So we will use that and then build a Y-bus for this 4-bus system. So, so let me share that file. So this is the data that you are seeing on your screen. That is from bus is 1, to bus is 2, and the impedance is J0.15. So on, like that we have 7 lines. Line number 7 is between 2, 4. So for bus 1, this is an old file, I am just editing it. And this is the first line. Then the next bus, let me just resize the window so that you can see it more clearly. The next bus is 2, 3, and the impedance is J0.05. The next bus is between again 1 and 2, and the impedance is 0.15i. So this we have done in the last class, the data. So please refer to that. I'm just entering the data. Nothing difficult here. Then another bus 4, 2. So again 0.20i. And then there is another bus 1, 4, and there is the impedance is 0.15i. And finally, there is a last bus 2, 4, and the impedance is 0.15i. So this was the program. System size is a 4-bus system, and here this is what we have done. So just a small variation I like to do here. That is, because we have double circuit lines and triple circuit lines, I just have to I have to take the existing data and then add to it. So that is what I have to do. I'll just share this code with you. So later on you can check this code, and then finally the Y-bus we are trying to create. So let me just execute this program now. So on the screen your right side, for our randomly generated system, we are able to see the Y-bus matrix. So Some of the elements in Vibers, I'm getting real numbers. So that's why I'm a little bit worried where the problem is. Okay, so now we got it. So on your screen, what you're seeing is the Vibers for our system. So here, this minus 20, 13, these are the first two columns of the Vibers, and this is the third column and the fourth column of the Vibers. So here is the Vibers of the system. So this was the code which you had done already, maybe back in lecture 7, 8, 9, how to generate a Vibus. So this is already done. So now I have all the values of y11, y12 up to y44. So these are y elements of Vibus matrix. So what is the next step? So the next step is we have to write the load flow equations. So before that, let me also enter the generation data. So I have the, on your screen, let me now share the data screen. Shortly you'll be able to see the screen. So this is the data we have created Vibus using this data. So now Vibus is created. So what is the next step once a Vibus is created? If I go down, so I have the generators and I have some values that I already know. So, so in our problem we had, if you remember, if you go down, we had selected bus 2 as the slack bus. So this was done in the last lecture, if you again recollect. So bus 2, that means I know V2 and delta 2. But what I don't know is the delta 1, delta V3, delta 3, these are all unknowns. So for knowing that unknowns, see these were the unknowns. Last class I already discussed. So to know these unknowns, we have to write these three equations. But then we also have to write the Q, that is the reactive power equations also. So last class we have written 5 equations. So we will try to solve them. But meanwhile, I have some data available. So that data I will enter. So for example, if I go up, so this is the net power. So net power injected at pi. So that is minus 0.5. So and then magnitude of V1 also it is there. So like this we have some data already available. So this data we can enter and then finally we can do that. So now let me also show you the equations. So equation 1 is on top, equation 2 is here, equation 3 is here. Solve iteratively, then we'll be able to get the Y bus. So, but then I realized that, due to lack of time, I will not do this today. I'll prepare the code for this and then I'll directly send it, because it is writing these equations is the important part which we finished in the last lecture. Right now, just we have to type this into the MATLAB and then we run it and we'll get the result. So what I'll do is I'll create this code and then I will share this code to you. You also have the link to our homepage. Using that, you can download the code and you can execute the program yourself and you can check the results. So, due to the best interest of time, I would like to continue with the next topic, that is Newton-Raphson load flow. So, I thought I will do it in today's class, but then I realized it is better to, uh, because since the equations are big, it's better to write separately and then share the code with you. So, so far, do you have any doubts regarding Gauss-Seidel load flow? we had solved one example problem and then we had created one more problem, and in that second problem we had taken slightly bigger one and the equations I have written on the board. So it's just a matter of typing these equations into MATLAB and then solving it. So again I ask you to solve it once again, and then if you have any doubts you feel free to ask me. Today I will try to start another topic, that is Newton-Raphson load flow. Very similar thing we will be doing in that, solving a load flow problem. But then the method is quite different. So if you have any doubts on GS load flow, let me know right away. Or you can also mail me separately. The NR method. So NR method is useful for solving functions which are in the form of f of x equal to 0. So where x is the unknown and I want to find out where the function value becomes 0. So to find this one of the, so as an example, sometimes a couple of lectures back I had given an example where I'll write sine x is equal to 0.1 x. So and then I'll say, so 0.1 into x. So this is the equation. Solve for x. So means at what value of x this condition holds good. Sin x value is equal to 0.1 of x. What is the values of x for which this condition holds? So there are many solutions for this. So what are the mainly solutions? So for example, x equal to 0. So sin 0 is 0 and then 0.1 into 0 is 0. So is a solution. But to understand this, we can also actually draw the graph of it, then we'll be able to get a better picture. So something like this. So this is the x-axis and this is the y-axis and this point is 0. Now I'll take the right hand side. So what is that? 0.1 into x. That means the slope is 0.1. So this is the form of y equal to mx. So this is a straight line passing through origin. So if I substitute x equal to 0, it is the origin point. And if I substitute x equal to 10, 10 into 0.1 is y equal to 1. So let's say this is 1. And then somewhere here, I'll say x equal to 10. So this is the line that I'm going to get. So of course, the same line will continue in the minus x-axis direction. Now look at the other equation. So what is the other equation? I have sin x. So sin x is a sinusoidal wave which is keep on changing. So let's say this is pi, this is 2 pi, and this is 3 pi. So I think 10 I have to adjust it such that, so this is 5, right? So 3.14. So this is my pi and this is my 2 pi. So this is 6.28 and then let's say this is 10. So what is a sine wave? The sine wave will start somewhere like this and then at pi by 2 it reaches maximum value and at pi it becomes 0. Then again at 3 pi by 2 it reaches minus 1 and again at 2 pi it becomes 0. And then again it reaches somewhere like this and then it comes down like this. So 3 pi. So 3 pi, let's say if it is here, 3 into 3.14. So it's close to 10. So somewhere, something like this. Now if you note, I'm getting one intersection point here, I'm getting another intersection point here, another intersection point here. and then another intersection point here. So so this is 1, 2, 3, 4 solutions are there already. Similarly, if you go to the negative side, so the negative side also you will find 3 more solutions. So 1, 2 and 3. So ahead it will be there. So uh, to get a clear picture, let's plot it accurately. So instead of approximately drawing this, let's plot this function accurately and then we'll be able to see it. So, so the two things that I'm interested in is sin x and then 0.1x. So let me go to my MATLAB interface. So I'll just give that. Just a minute. So okay, so this is the one function which I plotted. I'll just make hold on and then I'll plot one more function. So I'll show you the plots. Just for the time being, I'm just showing you the code. This one also I'll plot from -12 to +12. And then again I'll try to specify line width. Okay, so I got the plots. Let me now just show you the plots. I'll say give X label. So X label is, I think it's understood. So let's look at the plot itself. So let me share the plot. So I think now you are able to see the output of the program which I have written. So this is the plot that you are getting. Now this point that is there at the center. So this is the x equal to 0, y equal to 0. The blue line is the sine wave, both back left negative side and the positive side, and the red line is the another wave, this one. So how many solutions are there? So you notice 1, 2, 3, 4, 5, 6 and 7. There are 7 solutions for this problem. So when I solve this problem, sin x equal to 0.1x, I'll get 7 different solutions. So we will try to use Newton-Raphson method to find out some of the other solutions. Now, just approximately you notice where are the solutions. So if I zoom in, just I'm zooming the first part. So you notice that here there is an intersection and the value is somewhere near to or less than 3. So near to 2 or less than 3. So that is one answer. So remember that. Another answer will be somewhere near to 7. So you see this point is between 6 and 8. So near to 7 there is another point. And above 8, so maybe 8.5, there is another. Also, I'll have 3 more solutions and 0 is the another solution. So this is, I just plotted this for you to just get an idea. Now, I'll also show you one more plot. So I hope you understood this plot for sin x equal to x. So 0.1 into x. Now let's rewrite f of x equal to sin x minus 0.1 x equal to 0. So basically, if these two values are equal, I can just write it as a 0. I have to write it as f of x equal to 0. So then it is convenient for me to solve the problem. So now let me explain Newton-Raphson method. So what Newton-Raphson method says is that consider the plot. So by the way, before going to this Newton-Raphson method, I'm sorry, let's plot f of x. So what is the plot of f of x? So I have to simply say plotting of f of x. So let's do that. I come back to my program. So this time I'll just do only one plot. And instead of sin x, I'll just plot sin x minus 0.1 into x. So combined function here f of x I'm writing. So if I plot this, so just I'll execute this. So I got an output like this. Here you see 0. This entire line is the x-axis. At how many points is this line touching the function? So this is entirely the function. So behind the function will be above the x-axis. After this, the function will be entirely below the x-axis. At this point, there are 7. See, this is 1, 2, 3, 4, 5, 6, and 7. At 7 different locations, it is intersecting the x-axis, f of x. So that means these are the 7 solutions. These are basically the same functions. I have just plotted it in a separate way. I plotted them as combinedly one function. So you can see on the top minus sin x. This is sin x minus 0.1 into x. So this is the plot for this. So the function is something like this. So wherever it is cutting the x-axis is the solution. So this is the x-axis and this is the function f of x. So f of x equal to 0 means wherever it is cutting x-axis, that is the solution. At solution, f of x cuts x-axis. Now, this one, let's look at any one of this. Let's say this point. Let's say this point is the solution denoted as let's say solution is denoted as x1. Whereas my initial guess is, let's say this one. So I'm at this point. So this is x0. So starting from x0, I want to go to x1. So that is my objective. So that is, with that, let me explain the NR method. So the NR method starts from the definition of df of x by dx. So everybody know what is the definition of differentiation of a function. This is nothing but change in the function divided by change in the variable. What is the change in the function? So if I look at this, so the change in the function is, let's say my expected value is f of x1. So, but my present value is f of x0. And this one will be x1 minus x0. So, of course, this is not exactly correct. This is approximately correct. So what is df of x by dx? Is nothing but delta f by delta x, where limit delta x tends to 0. So this project or this formula will work only when this gap between x0 and x1 is very close to each other. So x1 is the actual solution, x0 is my initial guess. So if both of them are nearby, only then this equation will work. So delta x should be almost tending to 0. So that means it should be close to the solution. Now this is the equation. So let's call this equation 1. So from this I want to find out x1. So from equation 1 find x1. Because x1 is what is unknown. Why I am saying like that? Let's say x0. x0 you already know, because you assume some initial value of x0. So this is again differentiated at x0. And f of x1 can evaluate the function. Now what is f of x1? You know that at the solution point this will be 0. So this also you know. So this is known, this is known, this is known, and this is also known. So everything is known, only unknown value is x1. So I can find x1. So how to find x1? So x1 is like this. F of x1 minus f of x0. This is there as it is, the numerator. This one will come in the division. That is d f of x0 divided by d of x0. And then this x0, and then here it will be plus. So I just rearrange. Okay, so this is directly coming from this. From 1, I get 2. So how I get from 1 to, I just take this I just take this term to the other side and I bring this term to the denominator. So these two I changed, and then x1 I bring it to the right hand side. So I get this equation. Now in this we know f of x1 should be 0, because this is what is my definition of the actual solution. Where it intersects, there is a solution. So this term is 0. So I get further simplify, x1 is nothing but x0 minus f of x0 divided by d f of x0 by dx0. So this is nothing but the Newton-Raphson method. So I can generalize this and then write xn equal to, xn plus 1 equal to xn minus f of xn divided by f dash of xn. So f dash nothing but differentiation of the function. So this is the Newton-Raphson method. So this equation, if you remember, then it is sufficient. So how does the equation come? Just very simple, just only one step. I have written down the definition of df by dx, and then this is the approximation of df by dx, nothing but delta f by delta x. And then as long as these two values are close to each other, it will work. So let's now implement this. So let's now implement this. How to implement this? So I come to my MATLAB program, and then I will implement. Let me display a message. Solving sin x minus 0.1 into x using NR method. So this is just display a message. So now what is the first step? I just write down the initial solution. So my initial guess, let's say it is 2. So then what is the steps? For m running a simple for loop for 5 times. So 5 times I am successively solving this. So what is the new value of x? So old value of x minus f of x. So what is f of x? Sine of x minus 0.1 into x divided by f dash of x. So what is the differentiation of sine x? It is cos of x. And what is the differentiation of minus 0.1 into x? It is nothing but minus 0.1. So simple, I have just given this one line equation. That's all. Our Newton-Raphson load flow program is completed. So now I'll simply execute this program and then we'll see what happens. So if I execute this program, so I am getting x equal to 3.3742, then x equal to 2.8449, 2.8523, 2.8523, 2.8523. So in fact, after 2 iterations, the value of x converges to this value 2.8523. So remember, this was one of our solutions. The point where sin x is intersecting x, I said just below 3 it is intersecting. So this is conforming. I have found one solution. So let me come back to my code. So if I magnify this figure, somewhere the first time where it is touching 0. So here, you can see, I think this point. So this is a point where it is touching 0. This is 2.85. So I find another solution just after 6. So somewhere near to this. So let's try that. So how to find another solution? Just the code is same. My starting point is different. So I'll go back to the code. Try to solve it. Just only I change the initial value. So let's give a comment here. Now if I take the initial value of 6 and then if I run the program, so I'm getting like this. So 7.0682 is the solution. So just by changing the initial value, I'm able to get a new solution. So that is also correct solution for our problem. So what are the other solutions? So what happens if I give minus 6? So now I am searching in the negative x-axis direction, that intersection point. So I am getting minus 7.06. What happens if I substitute minus 2? So again if I run it, so on the right you can see minus 2.85. And finally what happens if I select 10 as my initial guess? If 10 is my initial guess, so then I am getting 8.4232. So again remember there was one solution here, 10. So like this. So Newton-Raphson method is effective in this way, that you can find the solution by successive approximation using this particular one single function. F of that is xn plus 1 equal to xn minus f of xn divided by f dash of xn. Now the problem with the Newton-Raphson method is that it's always not guaranteed to find the best solution. So for example, if I take a very far away point, let's say if I give some point as 16 as my initial solution. Now if I run this program, so 14 is the solution, then 11, then 14, then 13, then finally again 15. So it's not able to find the final solution even after 5 iterations. So let's try increase the iterations. Let's take 20 iterations. But the initial solution is still 16. Again if I run it, so now after 20 iterations I found 2.8523 as the solution. So sometimes it happens like that. So but then the problem here is you don't know which solution it will come. So in fact for 16 the nearby solution is 8.4, but then the solution that we are able to find is 2.8. So that's why this Newton-Raphson method is only effective when you know the solution to nearest to the actual value, then you can use Newton-Raphson method and solve it. Okay, so I explained Newton-Raphson method using some different equation. So let's come to power system equations and try to solve using Newton-Raphson method. So I hope you got some idea about how to use Newton-Raphson method. So any doubts or any questions so far on Newton-Raphson method? Okay, so if you're not having any doubts, let me continue. So I have a doubt. So the doubt is like this. The above method explains NR for one unknown with one function. What if I have two or more unknowns and functions? So then how to solve? So for example, in the variable of x and y equal to 0, another function f2 again in the variables x and y equal to 0. So I have two unknown variables x comma y and two functions f1 f2. So but then see, if it is a straight line equation, you know how to solve it. But then if it is not a linear and if it is a non-linear functions, how to solve it using Newton-Raphson flow? So quickly reviewing, if I have just only one function, then this is a procedure. If I have only one function, f of x1 equal to 0, then this is a procedure. So what I do is I'll simply generalize it. So something like this, x comma y n plus 1 equal to, or let me write it in the matrix form, xy n plus 1 equal to xy n plus 1, I'll write it here, equal to the old value of xy minus, I'll just take a function like this, f of x1, f that is f1 of xy, f2 of xy divided by what is known as a Jacobian matrix. The matrix is something like this. Now, because we have to differentiate, okay. So for differentiating, we have two functions and then we have two variables. So 2 into 2, 4 combinations are possible. That is differentiation of function f1 with respect to x. Similarly, differentiation of function f1 again with respect to y. So here you will take dx, x as a variable, y as a constant and differentiate this function. Here you will take y as a variable, x as a constant, again differentiate the function. Now I have another function. So d of f2 x comma y divided by dx, and then differentiation, it's actually partial differentiation. So x comma y with respect to dy. So like this division means actually you have to do invert of the matrix and then multiply it. So invert this matrix and then pre-multiply with this matrix. Then you add it to this, then you'll get it. So for example, if you consider this as a J matrix, then I'll get it xy equal to, so this is xy of n. The old answer, new answer. So this is Jacobian inverse multiplied by f1, f2. So something like this we have to do. Okay, so let's continue our analysis and then let's come to our power system. So the doubt that I just clarified is about two or more unknown variables. So I think you can extend this. If there is a third equation f3 of xyz, whereas f1 of xyz, f2 of xyz, so then you will be able to do that again in the same way. Here you will get a 3 by 3 Jacobian matrix. Anyway, so let's continue. To solve load flow problem. So this is the question I'm asking. So for doing this, let's do a quick review of power flow equations. So remember, some 2-3 classes back we have derived power flow equations. Second time I repeated, now third time I am repeating. So at the time I also told you to go to your home and then repeat it 5-6 times. So the more you power flow equation start, I'm just repeating it to you. I could have directly copy pasted the equation, but I want to derive it once again. So 5 times you repeat it, 10 times you repeat it, it is only beneficial for you. So let's do that. So Ohm's law for networks with AC networks. So what you get? I bus equal to Y bus. Seen many times. So this is n rows one column, this is n rows n columns, and this is n rows one column, where n is the size of the system. So what is the next step? Take row number k. So if I take the row number k, then I yk1, yk2. This is just the row. Ykn multiplied by v1, v2, vn. Or in other words, Ik equal to summation of I equal to 1 to n yki vi. This you are familiar with. Now this is equation A. So what is the other equation for Ik? Net power injected is nothing but net complex power injected at bus K from external divided by Vk. Both will have the conjugate. So this one, if I equate to the other one, then I'll get Sk conjugate is nothing but Vk conjugate multiplied by I equal to 1 to n yki vi. So this is equation B. So this from A and B. I get this. So finally, what is Sk? Is a Pk minus jqk. So why I am giving minus sign for j? Because of the conjugate here is equal to summation I equal to 1 to n yki vi vk star vk conjugate. So this is the these are all complex numbers. So now if I separate out real and imaginary parts, so what I get? pk equal to, I want to get only the real part. So I equal to 1 to n yki vi vk magnitudes. Just multiply the magnitudes and then find the cos of theta ki plus delta I minus delta k. So this is, many times we derived this. So once again, I am deriving this. This is the power flow equation. What about the qk? So I'll have the minus sign, then I equal to 1 to n, then I get yki vi vk magnitudes, then sine of theta ki plus delta I minus delta k. So this is the equation for qk. Now I want to write it in the form of equal to 0. So if I am looking for 0, so then simply I take pk to the other side and then here I'll put 0 here. So 0 equal to, why I am writing 0 equal to? Because Newton-Raphson method requires function value to be 0. Yki vi vk cos of theta ki plus delta I minus delta k. So this is one sorry, I run out of space. So just a minute. I'll just adjust this. So 0 equal to minus pk. So this is one. This is one equation. 0 equal to minus of I equal to 1 to n yki vi vk sine of theta ki plus delta I minus delta k minus qk. So this is my second equation. So I have two equations which are equal to 0. So this I can write it something like function, and the function name pk, and the variables are vn equal to 0. So in fact the variable here is only vk. Let me write v1 to vn equal to 0. Similarly, function qk, variables v1 to vn equal to 0. So for k equal to 1 to n. So now if I write how many functions? So number of functions you see, here you see only two functions, but that is for bus number k. One function for active power P and another function for reactive power Q. But then there are n, so totally there are 2n functions. And they are non-linear because sine and cos is there. We also have the magnitude, sine, cos and all these things. Now how many variables? How many unknown variables? So V1, V2, V3, Vn, these are all unknowns. So, but then you have V1 delta 1, V2 delta 2, and so on up to Vn delta n. So these are all unknowns. So actually, for if you look at it in the polar form, two unknowns are there for each bus. So there will be 2n unknowns. So we have 2n functions and 2n unknowns. They are all interrelated. Therefore, we will be able to solve it using the Newton-Raphson load flow method. And I can just take the initial solution, initial guess of all voltages equal to 1 angle 0. Because we know that the voltage will be more or less near to 1 per unit and angle will be more or less near to 0. If I assume that as the initial solution, and then I can solve it. So let's take an example problem and then solve using Newton-Raphson load flow. So these are the two equations. So this is NR equations. Actually NR functions I'll write. Or I'll write it in more functions for Newton-Raphson load flow. Before we go forward, let us do some kind of differentiation also. So I want to differentiate these functions. So let me repeat it once again here. So what is the first function? The first function is fpk equal to 0, which is equal to sum of I equal to 1 to n yi vi vk cos of theta ik plus delta I minus delta k minus pk equal to 0. Now, if I differentiate it, what will I get? Differentiation of fpk with respect to what I want to differentiate. So let's say, here this is the unknown variable and this is the unknown variable. So these are the two unknown variables. Other things are all considered as this one. So first I will differentiate with respect to Vk, or first I will differentiate with respect to delta k. So then what I'll get? Now when you differentiate with respect to delta k, this is the coefficient. So this coefficient will remain same. Now the cos differentiation is sine. Minus sign here, it will just simply become the sine. So the differentiation is nothing but I equal to 1 to n yki vi vk sine of theta ik plus delta I minus delta k. That's all. So this differentiation of cos is minus sign, but then because this minus of delta k is there, it becomes plus. So this is the differentiation. Now pk is a constant, differentiation of constant is 0 and everything else is 0. So this is my differentiation of function pk with respect to delta k. Now if you actually notice, this is nothing but minus qk, but that is another detail, we'll come back to it later. I want to differentiate the function pk once again with respect to now Vk, the voltage of bus k. So go up. So if Vk is the variable, and then if I differentiate it, then I'll get all the terms where except Vk will not be there. So it is like differentiation of some coefficient into Vk. So I'll just get I equal to 1 to n. I'll get all the terms as it is, yki vi, vk will not be there, and I will say cos theta ik plus delta I minus delta k. Now pk is a constant, so differentiation is 0 and then rest of thing is 0. So this entire thing is nothing but differentiation of the function with respect to Vk. Similarly, I can differentiate the other function. So what is the other function? That is function of qk. So what is qk function? This is minus I equal to 1 to n yki vi vk sine of theta ik plus delta I minus delta k minus qk. So this is our function is equal to 0. Now this function, now again I want to differentiate with these two variables. Differentiate the function qk with respect to the variable delta k. Now if I differentiate this entire with respect to delta k, so differentiation of sign is cos and delta k has a minus sign. That minus sign will cancel out this outside minus sign. So finally I will get like this, I equal to 1 to n yki vi vk cos of theta ik plus delta I minus delta k. That's it. Differentiation of q is, because q is constant, it will be 0. Now again, what is the differentiation of this function fqk with respect to Vk, the voltage magnitude of bus K? Then Vk is just a coefficient, everything else is considered as constant. So it will be nothing but simply minus summation I equal to 1 to n yki vi. Vk will not be there, just you will get sine of theta ik plus delta I minus delta k. So to summarize it, if I write it as a Jacobian matrix, so let me write it as a Jacobian matrix, that is differentiation of active power Pk with respect to differentiation of delta K. Similarly, differentiation of active power Pk with reference to magnitude value, the magnitude of voltage Vk. Similarly, differentiation of reactive power Qk with respect to delta K, and then differentiation of reactive power Qk with respect to Vk. Now the last term you see, this is same as this one. So this is nothing but this one. So if I further simplify this, if you look at the structure of this is nothing but Qk divided by Vk. So if you just go up, see this one, you have Qk. So if I divide by Vk, so I'll get everything except Vk. So yki vi sine of this, and then with a minus sign everything. So this is the term. So I'll write it here. Qk divided by Vk. Similarly, this will be Pk divided by Vk. So look at this one. This is nothing but Pk divided by Vk. So you can just verify. So you go up, you divide this term by Vk. So Vk will cancel. Everything else will be same. So that is what we have here. Now what about this term? That it is there here, you can see. This is nothing but Pk. Exactly. So this is Pk. And this is nothing but Pk. And then if you go up, this is nothing but minus of Qk. Because Qk will have a minus sign, so I put minus of Qk. This is my Jacobian matrix. So if you have all these values solved, you can actually, while writing a program, you can actually do this more easily. So anyway, so enough of mathematics. Let's choose a simple problem and then let's solve it. So far, any doubts you have? and then there is another line here, and then there is a load, and then there is a generator. So can someone remind me what is the values here? So I think V1 was 1000 at an angle of 0 degrees, and this one was J5 and V2 delta 2. But how much was this load? Revisit our challenge problem and solve it using. So can somebody remind me what was the values for S? 10 kilowatt plus J, 5 kVAR. Okay, so this is our problem. So now we want to solve this problem using Newton-Raphson load flow. So very straightforward, we can solve it. So let's see how to solve it. So first thing is I want to convert to per unit. Okay, so step 1, convert to per unit using S base as 10 k and V base as 1000 volts. So then what is my Z base? That is V base square by S base. That is nothing but this into this divided by 10 kVA. So this kilo and this will cancel and this will cancel, then I'll get 100 ohms. So therefore, my Z per unit for the line is nothing but J5 divided by 100. So I'll get J 0.05. So V1 delta 1 is equal to 1000 angle 0 degrees divided by V base. That is 1000 by 1000. So that is 1 per unit. So now my load is nothing but 10 kilowatts plus J 5 kVAR. So that if I divide by S base, which is equal to 1000, sorry, S base is 10 kV. Then my load is nothing but 1.0 plus J 0.5 per unit. So this is my load. So now let me draw the diagram in per unit. Network in per unit. So what do I get? J 0.05 per unit. V2 delta 2, this is unknowns. Then I have the load 1 plus 0 plus J 0.5 per unit. This is the load. And then this is the generation. So here the angle is 1.00 degrees. So that is step 1 completed. So what is step 2? Form the Y bus. So how to form Y bus? So because this is a bus number 1 and bus number 2, we have a 2 bus system. So I'll get 1, 2, 1, 2. Of diagonal element 1 by J 0.05 will be J20 with minus sign. The minus sign will be cancelled. So you have done this many times. This is my Y bus. Now step 3, write equations for P2 and Q2. Because P2, Q2 is given to you. So this is, so what is P2? Minus 1.0. What is Q2? Minus J 0.5. So because actually it is 0.5 itself. P2, Q2 are the power injected into the bus, but because this is a load, I have to give the minus sign. So I hope you remember this part. So write equations for P2 and Q2. So what is P2, Q2? So I equal to 1 to 2, Y2I, VI, V2, cos of theta 2I minus, plus delta I minus delta 2. So this is the equation for P2. So from this, I'm not interested in P1, so I'll just substitute I equal to 1 to 2. So I'll get P2 equal to Y21 V1 V2 cos of theta 21 plus delta 1 minus delta 2. This is one term, plus another term will be Y22 V2 V2 cos of theta 22 plus delta 2 minus delta 2. So this is my second term. So this is P2. Now, if you look at the Y bus, see this delta 2 cancels each other. Look at the Y bus and look at the theta 22. So if I go back to Y bus, this is the Y22 element. Here, the angle is minus 90 degrees. So what is cos of minus 90? So it is 0. So cos of 90 degrees or cos of minus 90 degrees is 0. So this entire term will become 0. So this entire term equal to 0. So finally, I have only one equation, that is P2 is nothing but the first term. Now let's write Q2. So what is Q2? So Y21 V1 V2. So I'll get a minus sign here. So I'll get sine of theta 21 plus delta 1 minus delta 2. So I continue the minus sign for this also, minus Y22 V2 V2 sine of theta 22 plus delta 2 minus delta 2. So here everything is same, just there is a minus sign and the cos is replaced with sine. Now if you come back, these two will cancel each other, whereas theta 22 is minus 90, sine of minus 90 is minus 1. So that minus 1 multiplies with this and becomes plus 1. So I'll get something like this. Q2 equal to minus Y21 V1 V2 sine of theta 21 plus delta 1 minus delta 2 plus Y22 V2 square. That's it. So this is my equation number 2. Now I will write it in the form of functions. So this is, let's call this as equation I, and let's call this as equation II. So how do I write it in the form of function? I want to equate it to 0. So P2 I take it to the right side, so it will become minus P2. So function of P2 is equal to Y21 V1 V2 cos of theta 21 plus delta 1 minus delta 2 minus P2. So this is one function. This value will be equal to 0 because P2 itself is equal to this. I have another function and that will be y21 v1 v2 sine of theta 21 minus plus delta 1 minus delta 2. There will be a minus sign here plus y22 v2 square minus q2 equal to 0. So this is my another function. So let's call this function as, yeah, we already have fp1, fp2. So these are the two functions, the above two functions. Let's substitute the values. Substitute known values. So what are the known values? So v1 equal to 1, delta 1 equal to 0. So this is given in the question. Similarly, P2 equal to minus 1.0 and Q2 equal to minus 0.5. This is also given in the question. Now what is Y21 and then Y22? So Y21, if I just created the Y bus. So when I created the Y bus, second row, first element is J20. So Y21 is J20. And Y22 is minus J20, like this. So these unknowns, if I substitute above, so what are the knowns? Sorry, these knowns. So the known values are Y21 I know, V1 I know, V2 I don't know. This I know, P2 also I know. So this is known, 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 and this is known. So only unknowns are V2 magnitude and delta 2 angle. These two are unknowns. That is what we have to solve. Okay, so let's substitute them. Now simple substitution. So function P2 is equal to Y21 J20 into V1 itself is 1, so I will not write it, into V2 cos of, what is theta 21? Theta 21 is 90 degrees. So 90 degrees plus delta 1 is 0 minus delta 2 minus P2. So P2 itself is minus 1. So minus of minus 1.0. So this is the first function. Now function Q2 is what? So again substitute it here. So minus of Y21 will be J20. V1 itself is 1, so I will not substitute. V2 is V2. Then sine theta 21 is 90 degrees. Delta 1 is 0 and then minus delta 2. Then this will be plus Y22 V2 square. So notice that we should not, by the way, I'm sorry, we should not consider J here because we are already considering angles. So this J is not required. Strictly, we are actually taking the magnitude of all three. Okay, so Y22 is 20 again. So the magnitude is 20 and V2 is the magnitude of voltage. So V2 square. And then Q2 is minus of minus 0.5 equal to 0. So let me further simplify. So if I further simplify, function P2 will be like this. What is cos of 90 minus theta? That is sine theta. So 20 sine delta 2, I'll write 20 V2 sine delta 2 plus 1 equal to 0. Then the second function is minus 20 V2 sin 90 minus theta is cos theta. Cos delta 2 plus 20 into V2 square plus 0.5 equal to 0. So I have two functions. So solve above two functions using Newton-Raphson method. So for that, I require, see what are the two functions? The first one is one function equal to 0, another function is equal to 0. Now I want to find the Jacobian matrix first. So how to find the Jacobian matrix? See, there are two functions and two unknowns. So first function is differentiate the first function with respect to v with respect to delta 2 and differentiate the first function with respect to v2. Similarly, differentiate the second function with respect to delta 2, differentiate the second function with respect to v2. So let's do that. So what is the differentiation? See, take the first function, differentiate with respect to delta 2. So if I differentiate with respect to delta 2, I'll get 20 v2 cos delta 2. That's all. This is a differentiation. Differentiation of 1 is 0. Now differentiate the first function with respect to v2. Then what I'll get? I'll get simply 20 sine delta 2. So this is my first function. Now differentiate the second function with respect to delta 2. Then this will be 0, this will be 0. Here differentiation of cos is sine, minus sign, but then there is already a minus sign. So it will become 20 v2 sine delta 2. Similarly, differentiate these other two terms will be 0. Now differentiate this entire with respect to v2. So I will get minus 20 cos delta 2 and then this will be plus 40 v2. So I have the now Jacobian matrix. Now what is the Newton-Raphson load flow? My new value, so I'll finally write the NR method. So delta 2 V2 n plus 1 equal to delta 2 V2. So this is iterations minus Jacobian inverse multiplied by f of P2, f of Q2. That's it. So this equation is what we are going to simulate in MATLAB or solve using MATLAB. So let's do that. So I have substituted everything and then we have all the enough material to go to my MATLAB interface. So I go to the class. So I'm creating a new file. Okay, so disk solving challenge problem using NR method. So V2 equal to 1.0, this is the initial value, and delta 2 equal to 0, this is again initial value. Assuming initial values. What is the next step? The next step is writing the functions, that is fp2, the function value of p2 is nothing but 20 into v2 into sine of delta 2 plus 1, that's it. Function q2 is equal to minus 20 into v2 into cos of delta 2 plus 20 into v2 square plus 0.5. So I have two functions I have calculated. Now I should also calculate the Jacobian matrix. So my capital J equal to, so it will have four elements. The first element is 20 v2 cos delta 2. We just now solved it. 20 into v2 into cos of delta 2. And the second element will be 20 sine delta 2. And the third element is 20 into v2 into sine of delta 2. And the last element is minus 20 into cos of delta 2 plus 40 into v2. So with this, the J is calculated. So once you calculate this, then what is the new value of, so I'll say VD2, I'll just define it as a matrix, is nothing but V2 delta 2, this is, I'll define it as a column matrix, multiplied by, minus inverse of Jacobian multiplied by FP2 FQ2, that's it. So V2 is nothing but VD2 of 1, and then I'm just updating the variables, VD2 of 2. This whole thing I'll put in a for loop. For I, so this simple 16 line problem, 16 line equation, in fact if I remove the empty line, challenge problem, let's run it and see what solution we get. If everything is correct, I should be able to get the correct solution. Okay, so once I run it, so here you see somewhere 0.922 and then minus 0.001 like that we are getting, and later on again it is not continuing further. So anyway, so I have let's increase the iterations. So it is not converging. I think there might be somewhere some plus or minus which I mistyped, and because of that it's not converging. Let me just check it and then I'll get back to you. So, but I hope you understood the general procedure how to solve a Newton-Raphson load flow. So I'll share today's notes and then I'll also share the all the mathematics is involved. You will have to you will have to practice it separately. So this is a method that I have just roughly outlined, and in the next class solution, and then maybe we'll try to solve more problems on it. So any doubts you have so far, you can ask, or since the time is so, I'll just end the class now. Thank you.